right. So I posted, there were two tables that are way too large for us to write out by hand. So in our week 9, the first note that I posted is it's just these big tables that we'll reference today. Okay, so talking about different numeration systems and a place value chart for later. So just so you have these to reference, I'll call them table 4.5 and table 4.7, just like they are here. So make sure you have that handy later. I'll bring it into our notes too. But okay, so where are we here? Ding, ding, ding. November. Crazy. A little delayed here. I don't know, it's 149, that's a different class. 139. Okay. So we finished logic last week as we were talking about, yeah, I'm excited to learn what the 13th month of 2020 is going to be called. Yeah, that's awesome. So we finished logic last week. We were talking about it's really to the power of 14 hard, right? It can be very difficult. So you do have to practice. I'm not gonna work you guys too hard with the logic. But everything that we covered last week will be tested, okay? So I'm committing to a test next Monday, okay? We'll call it a quiz. We'll kind of keep it breezy. So we'll call it a quiz on November. Yeah, it's a little fun quiz. So a little fun quiz. November 9th. Obviously 2020. I was gonna write 2020, but this year. And so we've got that quiz, and then just a heads up, yeah, 2020 is the song that never ends. So just a heads up, there's no classes on the Wednesday, the 11th, Remembrance Day, right? So November 11th, in case you have forgotten, is Remembrance Day. Oops. So there is no class. No classes, I should say, but for us, we have no class. Okay. So just a heads up. So that's why I want to do it on the 9th, and then you can have kind of a real day free of logic and bases and ugh, oh my. Okay, so that means on Thursday we're going to do a review. We might need a little bit of time to tidy up what we're going to start today. But on Thursday this week, hey, we don't meet on Thursdays. My customers already live without logic, and they're surviving. So let's see, what was I gonna say? Oh yeah, Wednesday. I don't know why I said, oops, Wednesday. November 4th? Yeah. Probably finish 4.3 if we haven't already. And test number 2 review. Oh, sorry. Little fun quiz. LFQ review. I take it back. It's a little fun quiz. Maybe there's a party emoji in the back to school basics? Okay, well, pretty basic here. But, yeah, I gotta get the party pack, but I think I'd have to pay for it, so. No, it shouldn't be cry-worthy. Well, we'll see. So what to expect on here. So for this quiz, for the LFQ, little fun quiz, we're gonna do, well, we've covered one-to-one and onto. Sorry, I have to have my cheat sheet here. Otherwise I won't remember. One-to-one and onto since then, since our last test. Focusing on one-to-one, right? Remember, a function has to be one-to-one in order to be invertible. So of course, I'm gonna kind of bake that into a nice, big, meaty question where you have to show that a function's one-to-one and then find the inverse and then show that it's the inverse using those function compositions where f composed with the inverse is equal to x and the inverse composed with f is also the inverse. So, or is also x. This LFQ is on November 9th. Here. Monday. Awesome. So, one-to-one and onto is kind of gonna get baked into compositions and inverses. Compositions and inverses. Well, we only have like less than 3 months of classes, so. TID terms. Exactly. So compositions and inverses, expect kind of one big question from here and then probably one smaller question. So here I would guess kind of roughly 2 questions. Okay. Next section we went on to was 10.1 and 10.2, which are exponential and logarithmic equations. So exponential and logarithmic, oops, despite sounding it out, logarithmic equations. What did we do there? I don't know, we just learned about log laws and laws of exponents, which we kind of had a good handle on anyways, and the relationship between, yeah, log jams, the relationship between exponents and logs. How do we solve for x if it's up high in the exponent? You have to take the log to bring it down. Blah, 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 blah. There. Exponents and logs. Probably about 2 questions from here as well. I'm reserving the right to make them multi-part, but just kind of quick evaluate this, solve for x, little things like that. Then we went on to logic. 3.1, 3.2, and 3.3, which was logic, of course. Where do we start? Truth tables, truth values. Now I can't remember. Conjunctions, disjunctions, and or negations, not. And just kind of these compound statements, compound logical statements. I'm gonna go for probably 2 questions from here. Remember, I'm kind of roughing it here. roughly 2 questions. Again, likely multi-part, right, where you set up one big truth table and figure it out. But what I'm gonna do, especially for the logic, these ones are pretty basic, but for the compositions and inverses and for the logic, but also the bases that we're about to cover today, I'm gonna set them up very similarly to the final exam so that you'll have seen it kind of multiple times, and it's not gonna, so even if you don't feel good about this test, work towards this test, but also know that you'll have a chance to do it all over again on the final exam, right? So I want to kind of use this to prepare you for the final. Okay. And then today, we're going to do 4.2 and 4.3, which are numeration systems. Numeration systems. Probably about 1 question from here. Of course, we're only spending 1 day on it so far. I suspect we'll kind of bleed into next day a little bit, but not too bad. Okay, so this one is going to be different. So last time you got your questions and you just did your questions in WebAssign, and then you sent me your work and I just went through and kind of checked your work. This time, I'm going to post a PDF for you at the beginning of our class time next Monday, and then you're going to work through that PDF and then upload your work to Gradescope, and then so your only grade will be the Gradescope grade. Because a lot of these aren't in WebAssign, but also because I don't want to hinge everything on just your final answer, because a lot of it has to do with procedure. Oh yeah, no, so you'll still have just our class time to do it. I'll give you 20 minutes, half an hour to finish up and submit it on top of that. So I'll give you guys kind of, what time do we go till? 2 to 4, well, 3:50, probably 4:15 to submit it on Gradescope. Right, you should be making sure everything is nice and clean, but I'll give you time to scan it and just kind of upload it on time. So a PDF of the quiz will be posted on Moodle. At the beginning of class time. Work through the problems. Of course, how else would you do the quiz? Work through the problems and submit on Gradescope. So submit all your work on Gradescope by 4:15. And submit your work on Gradescope by 4:15. Oops. People get confused when I use the 24-hour clock. 4:15 p.m. Okay. So I've given you a little bit of extra time, but honestly, you shouldn't need all that time to scan your work and upload it to Gradescope, especially because you've already done it once, but just in case. Okay. If you have a class after this, right after, then especially because it's a little fun quiz. So if you have a class after this, does anyone have a class after this? Maybe in the chat. Oh, a lab right at 4. Okay. Okay. I'll keep that in mind. Try to make it not too long. Okay. All right. Good, good, good. So, make sure I told you everything that I needed to tell you. I posted homework already on WebAssign for 4.2 and 4.3. And it's due November 9th at midnight, 11:59 p.m. So homework for 4.2 and 4.3 due November 9th at, of course, 11:59 p.m. Oops. Okay. Kelowna time, hopefully. Yeah, if it is doing 10:59 your guys' time, then let me know. But I think it's been okay. I think it's just been, no one's been pushing the clock maybe. Going right up until midnight. But yeah, sometimes it's not clear which time zone it's using, but anyways. And now daylight savings. For some reason, I'm like more tired today than usual. Even though we got like an extra hour, it's so bizarre. Anyways, I'm like, yeah, it's really confusing. Yeah, I don't know. Anyways, the extra hour made you oversleep. Yeah, exactly. Maybe that's the problem. Too much sleep. Anyways. Okay, so I was talking about the Babylonian number system. I guess it's part of the, of course, I shouldn't say I guess, it's part of the early numeration systems, which is in section 4.1, which is actually a really fun, leisurely read. But we're not going to cover it. So if you want to learn about just kind of different numeration systems, it's really interesting. It's really fun. Then have a look through 4.1, but obviously I'm not testing you on it or anything. We're going to move on to section 4.2, which is our enumeration system. But let's see here. Chapter 4 is on numeration systems. Okay. And just as a note, we're going to be doing 4.2, 4.3, 4.4, and then it'll make more sense when I say it later, but then we're gonna tack on some stuff that's not in the textbook, just elaborating on the octal and the hexadecimal system, which is base 8 and base 16. So we're gonna talk about base 2 a lot in 4.4. We talk about base 2 kind of in 4.3 as well, but so that's what's coming up, just so you're aware. But we're going to talk about all these bases, converting between bases, but before we do that, we're going to start and we're going to focus on 4.2 and 4.3 today. Okay. So 4.1 is just an interesting read on early enumeration systems. But it's not covered by us. Okay. So yeah, just kind of they've used symbols, and depending on where you were in the world, you use different numeration systems. And even the numeration system that we have today is fairly new. So let's talk about that. So 4.2 is our Hindu-Arabic numeration system. Hindu-Arabic numeration system. So how we think about numbers, how we count, and all that fun stuff, those are all our numeration systems. So even though, I mean, it sounds confusing, right? But this is the numeration system that we use, the Hindu-Arabic numeration system. And again, there's a really interesting kind of historical note about how things evolved. Even the number 0 took a long time to develop as kind of a positional thing, right? And so all these things took a long time to develop. And in fact, our number system that we use today took a long time to become common use. So all that and more in a fun historical note at the beginning of the section. But I'm not gonna blabber your ear off about that. I'll blabber your ear off about other stuff that I can test you on later. So the numeration system that we use today, the numeration system in common use today, I'll say, common use today is the Hindu-Arabic, it's a name, the Hindu-Arabic numeration system. It's often called the decimal system. So I'll make a note here. It is often called the decimal system. And of course, decim meaning 10, so it is base 10, which we'll get to in a little bit. But the decimal system has 10 symbols, right? So it has 10 symbols. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. These are all the digits that we need to construct other numbers, right? And we know these digits, and what's nice about this section is we develop things that we know in a way that's not obvious to us, but it's going to be useful for the next section when we talk about different bases, right? And so we're going to relearn how to count, essentially, even though we all know, you know, when I say 34, I mean 3 sets of 10 and then 4 units, right? And so, but notice how we're grouping in tens. So we're just going to go through all that again. We'll just kind of go from there. So we call these digits. They suspect. Digits are fingers, right? We have 10 fingers if we're lucky. And so, so that's where it came from, right? We have 10 digits, fingers, and so that's where the name came from. 10 fingers. I was reading something online where there are some kind of, yeah, course prereq, preschool math, yeah, 10 fingers, 10 toes. We could have been working in base 20 this whole time. Why didn't we think of that? But I guess there are some tribes, I guess, that use base 8 as their counting because they use the spaces between their fingers instead. So kind of interesting how these different bases kind of come to play. I haven't seen Avatar, I know, shame on me, but I guess they only have eight digits, so they work in base 8. Anyways, I'll have to watch it before I say anything more. Base 12 is based on the segments on the fingers on one hand. 1, 2, 3. It works out. Hey, that's awesome. Turns out the answer is right in front of us. That's awesome. All right. So, okay, so we're talking base 10 here, essentially. But I will say, see the start of this section for some fun historical notes. But don't worry, not covered. It's just interesting to know where things came from. Okay, so the decimal system, right, which is what we're calling this here. So our Hindu Arabic numeration system is also called the decimal system. I'll underline that. Okay, so the one that we know and love, probably, hopefully, is called the decimal system. So the decimal system is grouping by tens. Grouping by tens. So the idea here is we're going to develop everything from the ground up, grouping by tens. 10 total turbos. And then we'll apply it to different bases, but it's going to be the same kind of methodology that we're going to use. So the decimal system uses 10 symbols called digits, uses, oops, an important word is 10. 10 symbols as digits, or called digits. And then the larger numbers are expressed as powers of 10. So larger numbers are expressed in terms of powers of 10. Okay, so still working with 10. Okay. And we call it positional. So it's positional in the sense that 10 is different from 100, right? It's still got that 1 followed by a 0, and then a 1 followed by 2 zeros is different, right? And so that's what we mean by positional. So it is positional. One 0 is different from 1 0 0. So I'm just going to use dots because I'm not drawing squares, but if you have a hard time seeing the dots, let me know and I'll do better. Consider this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. The problem that we as people had initially was, what do we call this thing, right? And so what we did is, well, we had a couple of options. We could invent a new digit, Oops. Hey, spelling digit with 2 D's. Could be a cool way of spelling it. It's wrong. Could invent a new digit, or reuse the existing ones, which we know is what happened, right? We reuse the existing digits that we had to redo. Maybe that's what I should start calling them. Or reuse the existing ones by altering their position. By altering their position. Okay. So we know that 10, means this, right? It's a group of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What we're going to do is we're just going to block it off and call it a group. Call this a group. Okay. You know what? I'm going to add something here. We know 10 means one group of there. We call this a group. Okay. Okay. So far, it's nothing that we don't know, right? And so we can just emphasize that 10, well, the 0 here is a placeholder. To show 10 is different from 1. Right? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's one group, 10, versus just 1. So let's talk about things that we know. As we know, 32, right, is 3 groups of 10 and then 2 extras, right? We should feel pretty comfortable with that, hopefully. 32 is 3 groups of 10 and 2 extra. Okay. The 2 or the 1, we'll just call them extra because they're just extra little rogue units. They're not really part of any group, right? So what we have, right, we could go through and do tons of examples, but I think we have a pretty good idea of what, you know, all these numbers up to 99 would look like. And so we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just drawing out 32 dots and grouping them by 10. 32. Once we reach 9 groups and 9 extra, so 99, right? Then we have to figure out what else we can do. Well, we can make another group of 10 groups, right? So we can make a group of groups. So once we reach, a little tribute. Once we reach 9 groups and 9 extra, we do the same thing. We do the same thing that we just did and make a group of groups. And make a group of groups. So a group of groups is really 10 times 10, right? Which we can also write as 10 squared, which we know is 100, right? So that's where we get to 100, or the hundreds, is now you've got a group of groups, and then so on and so forth, and you can just keep grouping them. As soon as you hit 10, you make a group, right? And as soon as you hit 10 again, you make another group, so on and so forth. So, for example, what does 134 mean? Okay, so a little bit cryptic, right? But 134 we know is one group of groups, right? So 100, 3 groups, and 4 extra, right? So it means one group of 10 to the power of 2, right, which is 100. 3 groups of 10 and 4 extra. Okay. We can use this to write this out in expanded form. Okay, so expanded form emphasizes that 10 is our base, so 10 to the power of 2, and then 10, and then the extra is really just 4 times 10 to the power of 0. Remembering anything to the power of 0 is just 1, right? And so really what we've got here is 10 to the power of 1 and 4 extra of 10 to the power of 0, if you wanted to kind of continue with that pattern. So we use these the powers of 10 to rewrite this in what we call expanded notation. We can use this to write 134 in expanded notation. And I'll underline this because it's not a definition per se, but it is how you do the expanded notation. So if you're looking back, so 134 is going to be one group of 10 to the power of 2. So what we do is we do 1 times 10 to the power of 2 plus 3 groups of 10 to the power of 1 plus 4 groups of 10 to the power of 0. So 3 groups of 10 to the power of 1 plus 4 groups of 10 to the power of 0. Usually we don't write the 10 to the power of 1, we just write 10. But totally correct if you do 10 to the power of 1. And then 10 to the power of 0, we just kind of go away because anything to the power of 0 is just 1, right? So 4 times 1, you can just write 4. but I wanted you to see what it looks like in expanded notation. You don't need these brackets, but it sure helps, right? So if you're writing these out, it really helps to block off, here's my 100, here's my 30, and here's my 4. What if we wanted to write 52,613 in expanded form? So working our way from the right might be the easiest thing to do, right? Because what we're going to notice is that, okay, well, 3 is just on its own, right? So 3 times 10 to the power of 0, right? 1 times 10 to the power of 1, 6 times 10 to the power of 2, 5 times 10 to the power of 3, or sorry, I don't know if I said 5 or 2. Anyways, meant 2 times 10 to the power of 3, 5 times 10 to the power of 4. Okay, so I'm going to write this number out, but larger. 5, 2, 6, 1, 3. Okay, so here, this is times 10 to the power of 0. 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and 10 to the power of 4. Okay. So if you just write them out like this and start with your smallest number, right, or the ones, right, and start at 10 to the power of 0, 10 to the power of 1, then you can easily write this out. But you should always start with your largest number, even though we kind of started at 10 to the power of 0. Otherwise, I get kind of tripped up, right? 1, 2, 3, 4, 5, but because I've got 0 here, my highest power of 10 is going to be 4. That can get confusing, right? And so that's why I start on the right-hand side and work my way to the left. Okay? So in expanded form, we get 52,613 is what I meant to say. I didn't say that, but I meant to say it. Is 5 times 10 to the power of 4 plus 2 times 10 to the power of 3 plus 6 times 10 to the power of 2 plus 1 times 10 plus 3. I'm going to cheat a little bit. Keep it on the same line. Okay. Good. What if I wanted you to write, here, I'm going to scoot this up so we can keep it on the same, all these examples on the same page. It's just for me though. What if I wanted you to write, so now I'll give you something in expanded form and you're going to write it as a number. So write 4 times 10 to the 8 plus 9 times 10 to the 7 plus 6 times 10 to the 4 plus 3 times 10 plus 7 in decimal form. All right, so notice a few things, right? So our highest power of 10 is 8. 8, 7. I don't have any power of 6 or 5, right? I've got a power of 4, but then I don't have a power of 3 or 2 until I hit a power of 1, and then of course a power of 0, right? So you want to keep those in mind because those should be filled out still, right? And so what you get is you get 4, 9, so 10 to the power of 8, 10 to the power of 7, No, I would always do them in order. Thanks for asking, Riley. Yeah, so the question was, are there going to be questions where the tens are out of order? No. And in fact, you should make sure that you write them in order too. I'll always write them descending like this. So 4, 9, and then there's nothing times 10 to the power of 6, and then nothing again times 10 to the power of 5, and then 6 times 10 to the power of 4, 0 times 10 to the power of 3, 0 times 10 to the power of 2, 3 times 10, and then 7. So same idea, right? As 10 to the power of 0, 1, 2, 3. We know from scientific notation, if you have 10 to the negative 1, right, you've got a number that's to the right of the decimal, right? So a fraction, 10 to the negative 2 bumps you over another spot, I guess. 10 to the negative 3 bumps you over another spot after that. So a decimal point is used to separate the fractional parts from the whole parts. So here, 1 over 10, 10 to the negative 1. Yeah. 1 over 100 is 10 to the negative 2. 1 over 1,000 is 10 to the negative 3. Right. This is why we call it, instead of tens, we call it tenths, hundredths, and thousandths, right? That bumps you over to the right-hand side of the decimal. So if you've got a decimal kind of holding the fort here, let's say you've got a digit here, 1, 2, 3, 4, let's say. And of course, we could keep going all the way. We'll do the same thing on the right-hand side, 1, 2, 3, 4. And of course, I could keep going, right? And so these digits, remember, we start here at 10 to the power of 0. This one would be times 10 to the power of 0. This, whatever number is here, 10 to the power of 1. Whatever number is here, 10 to the power of 2, 10 to the power of 3. Okay. On the other side of the decimal, right now we've got a fraction. So now here we've got our tenths. So we've got 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, and 10 to the negative 4, etc. Right? So same idea on the right-hand side of the decimal as on the left-hand side, just keeping in mind that you have negative powers. Right? So for an example, what if we have to write 479.352 using expanded notation? Oh, I see. So for negative, we skip right past 0. Yeah, so the 0 is kind of holding the fort in the middle, and then it goes 1, 2, 3, and then it kind of ignores the decimal. It just happens to cozy right up to the decimal. So yeah, that can be a little bit confusing, but just remember that. Right? Famous last words. Just remember that. No big deal. Using expanded notation. So I'll give you guys just 2 minutes to work it out. and then we'll go through it quickly together. Okay. There are lots of ways that you could do this, or not lots, but I can think of, 3 ways that you could do this. I'm going to do it the same way that I was doing the other digits, the other numbers, digits. I'm going to write this out a little bit wider, a little bit bigger, and so I'm going to have 479.352. Okay? And then underneath here, I'm going to write kind of what place each of these are in. So starting from the decimal, I'm going to start with 10 to the power of 0, 10 to the power of 1, and 10 to the power of 2. So 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. Same idea, moving to the right now on the other side of the decimal. Right, I've got 10 to the negative 1, 10 to the negative 2, and 10 to the negative 3. So if I combine these, reading from left to right, we've got 4 times 10 to the power of 2 plus 7 times 10 to the power of 1, which you could just write as 10, plus 9 times 10 to the power of 0, which we kind of phase out, plus 3 times 10 to the negative 1, plus 5 times 10 to the negative 2, plus 2 times 10 to the negative 3, right? And so that would be the expanded notation for this thing. So 479,352 becomes 4 times 10 to the 2 plus 7 times 10. Technically, here kind of optional to the power of 1. If it helps you see it, then that's great, use it. Plus 9 times, and then I'll do the optional times 10 to the power of 0, plus, and then moving right along, 3 times 10 to the negative 1, plus 5 times 10 to the negative 2, plus 2 times 10 to the negative 3. Another way you could have written this out is to go first 400 plus 70 plus 9 plus 1 over, 0.3 plus 0.005 plus 0.0002, 002. Too confusing for me. Right, I like to just write them out like this. And so you could have broken it up into all their little components and then written them in terms of powers of 10. But you have to end up here anyways. So that's why I like to just write them out like this. But like I said, there are a couple of different ways that you could do it. If you got the same work as I did, you did it, right? And so why mess with a good thing if you've got it figured out in a different way? Okay. Any questions so far? Might feel weird to ask, how do we count to 10 type of questions, but we're doing a little bit more than that, right? We're thinking about it in a different way. So, all right. Then let's get into 4.3. Things are going to get weird. and we're going to try to work on developing just the way that we can deal with any sort of base. So not just base 10 like we were talking about, but any sort of base. Okay, so where's my next page here? Ah, not bad. 4.3 is on different numeration systems. Okay. So, different numeration systems, how to account to 10 starting from 1,000. I'm not sure I understand, but if you're starting at 1,000, 10,000? I don't know. So, yeah, if 1 unit is worth 1,000, I don't know. Gross. All right, so let's start talking about different bases. But first we'll establish that we don't necessarily work in just grouping by tens. So we don't necessarily group by tens, which is called base 10. We can group by any counting number. Any counting number. Okay, so the numeration systems that have been used and are used with computers specifically are base 2, base 8, and base 16. So depending on what you're doing, and you'll probably know or learn more about that than I will ever know. So I'm just here to talk about bases, and that's about it. So the numeration systems, but of course there's a reason you have to learn this stuff. The numeration systems used with computers are base 2, which is called binary, base 8, which is called octal, and finally base 16, which is hexadecimal. So these bases, of course, determine the groupings. The base determines the groupings. So if we had to count, no, let me just cheat a little bit here. Yeah, phew. If we had to count 11 things, right, in these different bases, well, we're going to group these things in base 2. We're going to group them in groups of 2. Base 3, of course, we're going to group them in groups of 3. And 4, we group them in groups of 4, and so on and so forth. So if we are to count something like 1, 2, and I'll make sure these are big enough here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. In various bases. We get something like And this is the first table that I posted on Moodle, table 4.5. I'm just going to copy that in here. Come on. These are our different bases. So if we're talking base 2, then what we get is, okay, we've grouped our groups of 2. And this is the one that I'm going to spend some more time on elaborating. But notice that for base 2, you only have 2 symbols, 0, 1, which later on we're going to start talking as if they're kind of on-off switches, which is what they are. 0 is off, 1 is on, right? And so it kind of switches back and forth as you move in by groups of 2, right? And so the symbols that you have to use, instead of 0 through 9, we only have 0 and 1, and then we cycle back over, right? And so the number 11, like we know it in base 10, is actually 1, 0, 1, 1, and then base 2. So we write the little base typically with letters, otherwise it can get really confusing, right? You could use numbers, but we spell out the base just so there's no confusion. Okay? Same thing with base 3. So now we have 3 symbols to work with, 0, 1, and 2. And so what we'll see is we can kind of cycle through, and we need to be able to show that we can have up to 2 left over. If we had 3 left over, that would make another group of 3, right? So you could lump those together. And so that's why you need to have 3 different symbols if you're working in base 3. Same thing with base 4, you have 4 different symbols, so on and so forth. And so the notation, right, is not the same for any of these bases. I don't think 11, 12, 13, 14, 15, 21, yeah. Shouldn't be, but just checking. And so the 3 can be a little bit tricky, right? So let's start with the 2, because I'd say it's the most confusing out of all of these. So in base 2, right, I'm just going to steal these 11 dots, and you can just use the ones you probably just drew out. Okay. Are they called base systems? I guess probably, unless that means something else. But if you called it base systems, I would know what you were talking about, and I would think it would be this, if that helps. So in base 2, what we're going to do is, just like we were doing in base 10, right? Instead of finding groups of 10 and lumping them together, we're going to find groups of 2. And so what I'm going to do first is I'm just going to circle groups of 2. 1 left over, that's all right. Okay. So then what I'm going to do is I'm going to group the groups of 2, just like we did when we were talking about 100, right? 100 is 10 groups of 10. Now, 2 groups of 2 can be lumped together. And so as long as we're working in base 2, right? So 2, 2. 2 is the name of the game here. Again, we've got another group of 2. This one can't be grouped with anything, so it's left out. So now I've got 2 groups of 2 of 2. Had to add those other 2. 2 groups of 2. What a mess. So anyways, here I can lump these together. You can use any base. So these aren't necessarily the only ones. You can go up to base 11, 12, 13, any base, as long as it's a counting number. Good. So now this green box, right, has bumped us from, so the blue circle, that was our kind of, well, this one is our first position. These blue ones are our second position. The pink ones are our third position. And the green ones are our fourth position. And so what we get is we get one green one. And then there are two pink ones. And so, but 2 becomes a 0. So it goes between 0 and 1, and then it switches back to 0. So because there's 2 of them, it's going to switch back to 0. And so here, you've got 0. And then we've got 1 left over. And then just one lowly basic one. Okay. So I'm rethinking if it's cycled through or because it's been absorbed by the green one. Either way, it works. So here, this is why we say, oh, it's 1, 0, 1, 1, base 2. Okay. It's going to be a little bit better once we start kind of working with it with not just little dots, right, with actual numbers. But we're getting there. So for bases higher than 10, the problem becomes that we have to invent new symbols, which is fine. We can use the alphabet. Some of them have, all of them probably by now have been assigned. So for bases higher than 10, we need to invent new symbols. We need to, quote unquote, invent. We're not inventing anything, new symbols. Capital T is a group of 10 as long as your base is more than 11, right? 11 or higher. It's a group of 10. Bases 11 and up. Capital E is used as to denote a group of 11 for bases 12 and up. Sounds like a game. Bases 12 and up. So for example, now until we get into hexadecimals, remember, are base 16. Until we get into hexadecimals, which is I think the last section that we're doing, I'm not going to worry too much about bases larger than 10. We're going to focus on bases smaller than 10. So we'll come back to this. It's going to be a lot anyways, so don't worry, but we will come back to it. So if I write 2 capital T base 12, what does that mean? Well, it means I have 2 blocks of 12. Am I really going to do it? Yeah, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm going to cheat and copy this out. copy, paste. So it's saying I've got 2 of these, and I have another one that's not quite a full set, but it's only 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's what it means. So like I said, we'll come back to that when we need it. Okay. Notice that in a base B system, so usually we talk about base B to denote any base, any counting number, right? In a base B system, you need to have B symbols, right? So notice in a base B system, we need to have B symbols, right? So base 2 had symbol 0, 1, right? So 2 symbols. Base 6, if you refer to that table that I gave you and I copied in, 6, base 6, we're working with symbols 1, 2, 3, 4, 5. Oh, sorry, 0, 1, 2, 3, 4, 5. And then, of course, base 10, we're working with 0 through 9, so we've got 10 symbols. 6, 0, 1, 2, 3, 4, 5. Oops. 6 symbols. Okay. So we haven't really done any work with bases yet. So our first stop is to change from base B into base 10. I'd say this is the easy way to go, and then changing from base 10 into a base B is a little bit harder, but not too bad. So change from base B to base 10. And just so you can find it later. All right. So we're moving from base B to base 10, and then just as a heads up, we're gonna have to move the other way in a little bit here. But to change from a base B, so to change from base B to base 10, we write the numerals in expanded notation, just like we were doing in expanded notation. And then the resulting number is in base 10. Oops, I guess I ended my sentence there. The resulting number is in base 10. So, for example, right in base 10, the first one we're going to do is 1011.01 base 2. And then what we're going to do is we're going to convert the same numeral, base 2, base 4, and base 5, right? Just to kind of get the hang of it here. Okay. They're all going to become different values in base 10, right? Which makes sense. So what we have is the same idea as when we were talking about the decimal system, right? And so here, and I guess I should have emphasized that earlier, but here we are. This is the 2 to the power of 0 spot. So what I'm going to do is I'm going to write this out bigger. 1, 0, 1, 1, decimal, 0, 1. So here, if I'm working in base 2, then what this becomes is this is the 2 to the power of 0 spot, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Same idea as before, 2 to the negative 1, 2 to the negative 2. Okay. So when you write this out in expanded notation, just like we did with the tens, right, you're going to write 1 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0 plus 0 times 10, 2 to the negative 1, blah, 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 plus 1 times 2 to the negative 2. All right, let's write those out. So 1011.01 base 2 becomes 1 times 2 to the 3 plus 0 times 2 to the 2. You don't have to write this one, that's just going to be 0. But I like to do it just so that I make sure I can go through and I can check to make sure I haven't missed one. If you want to drop it, that's fine, but I'm going to keep it. Plus 1 times 2 to the 1, of course you could just write 2 if you wanted, plus 1 times 2 to the 0 plus 0 times 2 to the negative 1 plus 1 times 2 to the negative 2. Okay. So these numbers all behave the same way that we expect them to, right? 2 to the power of 3 is 8, right? 2 to the power of 2 is 4. So what we get is to change from base B and base 2 in this case to base 10, write the numerals in expanded notation. So that's what we did. And then the resulting number is in base 10. Okay. So what we get is we get 1 times 8 is 8 plus 0 plus 1 times 2 is 2. 1 times 1 is 1, and 0 times 2 to the negative 1 is 0, plus 1 times 2 to the negative 2, which is 1 over 4, right? So 1 times 1 over 4 is 1 over 4, or we can work in decimals, 0.25, that's totally fine. So this, once we add them all up, 11.25. This is base 10. We don't have to write 10 here. That's the only base that we can assume. All the other ones we have to write. If it's a base other than 10, we have to write it. But here, of course, this is base 10. Let's do the same number, but base 4, right? Just so we can see how these things work. E 1011.01 base 4. Okay. So again, I mean, you could even start by writing it out kind of nice and big, and then putting, now instead of 4, you have, instead of 2, you've got 4 to the power of 0, 4 to the 1, 4 to the 2, 4 to the 3. I keep wanting to say 2. Right, and so here, I'm going to write it out expanded, so I'm going to use the same method that I was using before. I'm going to try to always use the same method. But if you have something that's working, then go for it, right? It doesn't have to be my method. It's the most common, I would say, but if you've got a way your mind works, go for it. 1011.01. So now I'm working in base 4. So this is 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3, 4 to the negative 1, 4 to the negative 2, filling it out that way. And because I want to keep it on the same line, how about or on the same page rather, I'll bump it up one step. And so 1011.01 base 4 becomes, so now I'm just rewriting this out same way I did. 1 times 4 to the 3 plus 0 times 4 to the 2 plus 1 times 4 to the 1. So here we go, 1 times 4 to the 3 plus, oops, 0 times 4 to the 2. Again, if you wanted to drop it, that's totally fine. Plus 1 times 4 to the 1 plus 1 times 4 to the 0 plus 0 times 4 to the negative 1 plus 1 times 4 to the negative 2. Okay. I have to use a calculator to know what 4 to the power of 3 is. I know you guys are probably quicker than I. 4 to the power of 3 is 64. Yeah. So 1 times 64 is 64. 4 to the power of 2 is 16. Doesn't matter, it's times 0. So plus 0. Guess I'm just showing off. 1 times 4. Not a Minecraft. No, I'm not. So yeah, just showing off over here. 1 times 4 is, oh, I almost said 1. That would be the end of my showing off. 4. 1 times 1 is 1. 0, well, 0 plus 0 plus 1 times 4 to the negative 2 is 1 over 4 to the power of 2, 1 over 16. So 1/16 is 0.065. Confirm. .25. Don't worry, the 2 made an appearance later on, so I was just sloppy in my notes. There. So this becomes, once I add all these up, I get 69.0625, base 10, of course. The last one we'll do is base 5, so base 5 to base 10, 1011.01 base 5. Same idea. I'm gonna write them all out kind of lofty, put my 5 powers underneath, 1011.01. Base 5. 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3, 5 to the negative 1, 5 to the negative 2. My 5 powers are bad. 5 to the power of 3, 1 to the 125. 125. So what we get is we get 1011.01 base 5 becomes 1 times 5 to the 3 plus 0 times 5 to the 2 plus 1 times 5 to the 1 plus 1 times 5 to the 0 plus 0 times 5 to the negative 1 plus 1 times 5 to the negative 2. Okay. This is 1 times 125, which is 125, plus 0 is just 0. 1 times 5, so plus 5. 1 times 1 is 1, plus 0, plus 1 over 5 squared is 1/25.04. So this becomes, I think, 131.04. Okay. So hopefully that part makes a bit more sense, right? Especially having seen it with the base 10, right? How we kind of start from the middle, just to the left of the decimal, and then we can kind of have our powers of 10 flowing out left and right, right? Kind of as big as I can say it, I guess, right? And then depending on the base, you do the exact same thing, and that's how you're gonna expand this thing out and convert to base 10. Now, going the other way, I would say is a little bit different, okay? So, if we have to change from base 10, oops, from base 10 to base B, and I'll underline this for later. Depends on the base, obviously, but the same method for all of these, right? So if we're talking about base 2, then you're gonna have to group by 2s. Base 3, you group by 3s. So to change from base 10 to base 2, base 2, we group by 2s. Base 3, group by 3s, of course, etc. So there are going to be 2 ways that we can do this, and it doesn't matter which way you use, as long as one of them clicks for you, use that one. I'm going to do both for the most part. I'm going to do both ways, side by side. But I want you to pick the one that makes the most sense to you, and then just stick with that one. You don't have to learn both. Okay. So there are 2 ways, or 2 common ways, to go from base 10 to base B. To go from base 10 to base B. The first one, and of course they're related, they kind of do the same thing, but just a different approach. So the first one is if you list all the powers of the base that you're interested in. So using a list or a table of powers, now let me see what I called it later. Yeah, using a list or a table of powers in the base B. Okay, so I'll show you what I mean here in just a little bit. The second option is to do repeated division. Repeated division. Okay. So the table or the list, it really only, if we're working in a single base, we don't need a table, we can just use a list. But the list that I'm talking about is in that handout that I posted. So I'm gonna grab this one here, copy, and uh-oh. Notice we were working in base 2, was it 3 and 4? no, 2, 4, and 5, right? So we already had to make use of some of these powers, right? We had to know that 2 to the power of 3 was 8, for example, right? We had to know when we wrote it out in expanded form, but you can just use your calculator, right? So this is not some secret thing. You can just use your calculator to figure this out. But what's hard is you'll need to kind of know these values. So if you're working in base 4, for example, it might be useful if you're going the table route. So the kind of the first option is to write out some of these common powers of 4, right? 4 to the 0, well, of course, is 1. 4 to the 1 is 4. 4 to the 2 is 16. 4 to the 3 is 64. 4 to the 4 is 256. See if you need anything bigger than that, but just to have kind of a table of values that you can reference. Okay. And so I guess I had to leave that space here. C table. Now I'm just filling in the space here, but C table 4.7 below, if using option 1. Right? A list of powers. Okay. So let's do an example, because that was pretty cryptic, right? We've got 2 different ways of doing it, so we can use a list of powers or repeated division. We'll need to brush up on our sort of long division, or you can just use your calculator, right, and just kind of go from there. But one way or another, we need to be able to do these conversions. So convert 42 to base 2. Okay. So what we have to do is, the first thing I'm going to do, first using a table or a list of values. Okay. That's the first way I'm going to solve it. And then the second way is I'm going to use kind of repeated division. So what I have is, if I've got base 2, then I need to have a quick reference up till 42 of my powers of 2. So what I'm going to do is I'm going to have, well, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 3 is 8, 2 to the 4 is 16, and 2 to the 5 is 32. 2 to the 4 is 16, 2 to the 5 is 32, and then 2 to the 6, just for reference, because what I'm going to do is I'm going to go just past 42. 2 to the power of 6 is 64. So here, 42, our number would fall somewhere in between here. 42 is somewhere here. Right, somewhere between 2 to the power of 5 and 2 to the power of 6. Okay. So what we're going to do is we're going to start with 2 to the power of 5. Right, what I'm going to do essentially is I'm going to take out a group of 32 from 42, and then I'm going to keep lobbing these things off. So from the table, or the list from the table, we see the largest value oops, value less than 42 is 2 to the power of 5, which is 32. So we can write 42 is one group of 2 to the power of 5. So we get 1 times 2 to the power of 5 plus 10. Okay. So here, right, this is 32. 32 plus 10 is going to be 42. Right? So I'm preserving that number, but I've rewritten 32 as a power of 2, right? 1 times 2 to the power of 5. So I'm essentially working backwards from where we were before, right? But now I need to deal with this 10, right? So here, we need to break this down. If you look at your list, okay, 2 to the power of 5, if I go 2 to the power of 4, I can't squeeze 16, a group of 16 out of 10, right? And so there's going to be 0 times 2 to the power of 4. Right? I can squeeze a group of 8 out of 10, right? Leaving me with 2. So what this is going to look like is a lot like division, right? Long division. Just kind of a different way of thinking about it. How did I want to write this down? So now try 2 to the power of 4, right, is 16. But we only have 10. Oops, we only have 10 left over. We only have 10 left over. So we have, oops. So we have 0 times, oops, base 10, 2 to the power of 4. Right. What we do is we can construct this in kind of a running list. We can put this into a running list. Right, so what we're doing is we're saying we're going to start with 42. 42 we decided started with, so just like how we wrote here, but then with the 10 left over, I'm going to move that over here and deal with that. And then I'm going to kind of keep going through my powers of 2, starting at 5. 2 to the 5, 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1. So I have 1 times 2 to the 5 plus 10. Now this 10 is going to move over here. 10 can't be written as a power of 2 to the power of, or as a multiple of 2 to the power of 4, right? We can't squeeze 16 out of it, is what we decided. So this is going to be 0 times 2 to the power of 4, which means I still have 10 to deal with over here, so plus 10. I haven't really dealt with those yet. So same idea, I'm going to move that 10, that same 10 over there. But once I've started at 2 to the power of 5, just like before, right, I need to go through every power till I hit 0. So this becomes, so 10, now I'm talking 2 to the power of 3. Multiples of 2 to the power of 3 is, well, 2 to the power of 3 is 8, right? That's helpful. So that's why I say it's nice to have kind of a reference. Once you know your base, you can quickly write out your powers and say 2, 4, 8, 16, 32, 64, and more if you needed. But 8, I can squeeze 1 8 out of 10. And so I get 1 times 2 to the power of 3. Oh, make that look like a 3. Plus 1 times 8 is 8 plus 2. Okay. Billie Jean loves base 2. Should get t-shirts. So now we deal with this 2. 2, don't forget about 2 to the power of 2 is 4. Again, I'm not able to squeeze 4 out of just 2. It's confusing because it's 2 base 2, but what we have, right, is 0 times 2 to the power of 2 plus that 2 is still left over. Running out of colors here. Finally, I'm going to get to deal with it. 2 is 1 times 2 to the power of 1. 1 times 2 to the power of 1. Okay, and my leftover here is 0, so plus 0. Remember, I have to keep going till I hit 2 to the power of 0, so you don't want to stop here just because you have 0 left over. Well, you can still deal with 0 here. What color can I use? Purple, maybe. Ugh, brown. Let's do that. Brown, brown. Is 0 times 2 to the power of 0. We must include all powers of 2. So that's why we have to go, if you start at 2 to the power of 5, 4, 3, 2, 1, 0, that would be a common mistake if you forget to include one of these just because you can't pull a 2 to the power of 2 out. Now here's the fun part, okay? Reading from the top down to the bottom, this is the number written in base 2. So 1, 0, 1, 0, 1, 0, base 2 is 42 base 10. Pretty cool. So here, oh, I guess it's a highlighter. Undo. Highlighter mode. Looks like I kind of wiped it out, but anyways. Read from top down, right? You get 1, 0, 1, 0, 1, 0. Base 2 is equal to 42 base 10. Or the other way around. Maybe that's what I should do. 42 base 10 is equal to 1, 0, 1, 0, 1, 0 base 2. Okay. The other option, which I would argue is doing the exact same thing, but sometimes one way is more useful to you. So the other option is, I'll just say, or we can do this using repeated division. I guess by 2, base 2. Okay, the repeated division, if you think about long division, right, we're gonna kind of put our number that we want to divide on the inside, and then we do a little curved kind of divisor, and then the number that we're dividing by on the outside. But how this is gonna, if we're doing repeated division, we're actually gonna stack it from the bottom. So you start with your biggest division on the very bottom, and you want to make sure that you have enough room above in order to do these repeated divisions. So here, I'll make a note. We start at the bottom. So we must make sure we have enough room above our initial division in order to complete all the repeated divisions. So we must make sure we have enough room above to complete all the necessary repeated divisions. Okay, so what I'm going to do is I'm going to start 1, 2, 3. Since I already have it and I'm running out of space here, 1, 2, 3, 4, 5, 6, 7 is what I need. So of course, all right, fine. I'll start down here. 42 is the number that we want to convert, right? So I just want to make sure that I have enough room up above here in order to divide this thing out by 2, groups of 2. So 2, and use your calculator for this, right? If you do 42 divided by 2, I get 21 even, okay? The key is to keep track of the remainders here. So in this case, there are no remainders, so that's fine. We can say the remainder is 0. So now we get 21, okay, with a remainder of 0. Okay. Keep track of the remainders. Okay, so now 21 is going to get divided by 2. So what I do is I just stack another divided by 2 on top of it. It's going to look weird, right? But 21 divided by 2, just use your calculator, right? I'm finding that it's 10.5. So it's 10 whole units. And so I'm going to write that up above here. And if you do 10 times 2, that's 20, so I have a remainder of 1, right? And so the remainder is 1. 10 is going to get divided by 2. We know 10 divided by 2 is 5, right? So this puts me at 5 here. My remainder is going to be 0, right? If I go 5 times 2 is 10. 10 minus 10 is 0. So I have a 0 remainder. I want to divide 5 by 2. 5 divided by 2, you probably know, right, is 2, 2.5, right? But 2 with a remainder of 1. Okay, so now 2 is going to get divided by 2. 2 goes into 2 one time with a remainder of 0. Don't stop until you have a 0 up here, okay? And so you're going to keep going until you've got 1 divided by 0, undefined. 1 divided by 2 goes into, so 2 goes into 1 0 times. Keep going until you have 0 here. Okay. 0 times 2 is 0, but I still have a remainder of 1. So that's where this remainder came from, or comes from. I'll put it on the same line here, remainder of 1. Now, the result, you read this from top to bottom. So 42 base 10, again, is 1, 0, 1, 0, 1, 0 base 2. Maybe I'll say the answer, you read down. Okay. So what we're saying is, again, 42 base 10, which is implied, but I'll just do it just for emphasis, is 1, 0, 1, 0, 1, 0 base 2. And I'm out of time, remainder 1. So we'll leave it at that. But what I want to do just for next day, write 42 in base 3 and 4. Oops. So just for next day, right, that's where we'll start with a review, and then we'll review for our little fun quiz, which will include this, but you'll be really good at them by that time. Hang loose. All right, awesome. Thanks, guys. I'll see you on Wednesday. Bye, kitties.